Okay, getting into chapter 5, we are now dealing with systems of linear equations, and we get a couple nonlinear equations when we get into 5.4. But 5.1, we're going to start with two equations with two unknowns, and we're going to have two different methods of solving those, the substitution method and the elimination method, and that revenue, cost, and break even is an application of those, one or both of those methods. Okay. Erase this. All right, so up to now, when we were dealing with linear equations, we only had one unknown. All right, so we talked about linear equations being straight lines, right? And that's what we're talking about in this section, are straight lines. Okay, so these are linear equations, and we call them systems of linear equations. But they are linear, so they are straight lines. So systems of two linear equations with two unknowns. So we're going to have two unknowns in an equation and two of those equations. Our goal in this section is to come up with the pair, the xy, that solves both equations. So we got three possibilities when solving these systems. When solving these systems. First, because we're talking about straight lines, right? So if we're talking about two straight lines, what we're going to be given is the equation of one line. That's going to be an equation in x and y. And then we're going to be given a second equation, which is going to be a second line. Our solution is going to be where they cross. That's going to be the solution. And in this case, we get one solution. When we're talking about two straight lines, the first possibility is we get a solution. That solution is going to be the point of intersection. Okay? That's probably the most common outcome. I don't want to say that, but generally in our situation, when we get a solution, it's the point where the two lines cross. Because think about, every point on this line has an xy combination that solves the equation of this line. Every xy point on this line solves the equation of this line. There's only one point, xy, that solves both of those equations. And that's the one we're looking for. Sometimes we won't be able to find a solution. And that's the case where the two lines are parallel. Right? So if we have parallel lines, there's no solution. When we look at the equation of this line and the equation of this line, there are no xy pairs that make both of them true. So that's a case where we have no solution. A third case is when both equations actually represent the same line. So when two equations are really the same line. So really they're just overlapping. Right, so both lines are overlapping, and we get an infinite number of solutions. So this kind of goes back to the cases, remember in chapter 1, where we talked about conditional, right? When we solved a linear equation and we got a solution, or any equation, but in this case linear equations, and we got a solution, we called that conditional. Right? It was conditioned on the fact that xy is this point. Inconsistent, we called no solutions, and identities we called infinite number of solutions. So these kind of apply to those same ideas. All right, so a couple different forms of questions that you'll see in this section. The first will be you'll be given two lines and asked if, you'll be given two lines and then a point, and you'll be asked if that point is a solution to the system of two equations. So something like that. We look at number 4 on page 527. Okay, you're given a system of two linear equations. Okay, we'll just call it a system of two linear equations with two unknowns. And that is these two equations. 5x minus 4y is 20. Call that equation 1. And equation 2, 3y equals 2x plus 1. So this is a system of two equations with two unknowns. Now it's generally a good habit to get into to line up your x's, y's, and constants. This one is not quite lined up, but since we're just checking this one, it's not so important. But it's a good habit to get into to rewrite like this. X is in one column, y is in the next, constants over here. So that one stays the same. I'm going to bring this x over to this side just so I can put it under the other x, leave the 3y where it is, and the constant over here. So that's just a good habit to get into. We don't really need to do that for this particular question, but again, good habit to get into. Line up the x's, line up the y's, put the constants on the other side. So the question here is we're given a point. We're given the point 8, 5. And the question is 8, 5 a solution to this system? So all you got to do here is plug in the x equals 8 and the y equals 5 into this equation. If it's not true here, you're done, because it has to make both equations true. Okay, so you plug it into this equation first. So we check, this is the x, this is the y. If I put it into equation 1, I get 5 times x minus 4 times y, and I want to know, does that equal 20? Well, I get 5 times 8 is 40, minus 20 does equal 20, so that one checks. Okay, if that one didn't, then you're done. You say, no, it's not a solution. If that one works, then it also has to work in the other equation. So now we put it into equation 2, and we say negative 2 times 8 plus 3 times y, and we want to know, does that equal 1? We get negative 16 plus 15, and that does not equal 1. Right? That equals negative 1, so our answer is no. It's not a solution. Where's the question? It's not a solution to the system. They both have to be true. Right? This one was true, but this one was not. Therefore, this point 8, 5 is not. If you were to graph these lines from our previous section, if you were to solve this for y, put it in slope-intercept form and graph it, solve this for y, put it in slope-intercept form and graph it, you'll see that this is not a point where they intersect. Okay? All right, so given a point, we want to be able to determine whether that given point is a solution. More importantly, probably, is coming up with the point that is a solution. Right? So that's what we want to do. And those are the two methods that we're talking about that are going to allow us to do that. So substitution method we'll look at first. Substitution method says, all right, so solving systems of two equations with two unknowns. We'll just say two equations here. We know it's two unknowns. So first method is the substitution method. All right, so both these methods, the substitution method and the elimination method, the idea is to take the original system of two equations and two unknowns and create one equation with one unknown. Solve for that one unknown, and once you know one of the two, it's pretty easy to find the second. Right? So the trick is to form one equation with one unknown. So the substitution method, let's look at an example here. Let's look at number 8 on page 527. We have a system of two equations. 2x minus 3y equals negative 13. That's equation 1. I like to label them so we can refer to them as we go. And the other one, I'm going to rearrange it first. It's not in the columns, like we said, we like to rewrite it, so I'm going to rewrite it immediately here and put it in the form that I want, which is 2x minus 2x plus y equals 7. All right, so let's say this is the given system of equations. And you're asked to use the substitution method to solve this system. You want to come up with both the x and the y. And then you can check it by using the method that we looked at in the first example to make sure that it's actually a solution. Triple on my shoe here. All right, so substitution method, what you do, you got two equations and two unknowns. So what you want to do is solve either one of the equations for either one of the variables. In this case, when you see one of the variables sitting alone, that's your best choice. Doesn't matter, you can solve the first equation for x, or solve the first equation for y, or solve the second equation for x, or solve the second equation for y. But after you do a few of these, you're going to see that when you have one of the variables sitting alone with a coefficient of 1, that's going to be your best choice. Doesn't matter, you'll still get the right answer if you do things right. But the easiest thing is to solve equation 2 for y. So you solve one of the equations for one of the variables. So equation 2 now becomes y equals 2x plus 7. And so all I did was take this equation and add 2x to both sides. Now, plug this in to the other equation. Plug this y into, and it's very important that you plug it into the other equation. If you used equation 2, you can't put this back into equation 2, it's not going to lead you anywhere. So you got to put it into the other equation. In this case, equation 1. So we put that into equation 1. Everywhere we see a y, we're going to put 2x plus 7. And in that way, we're going to create one equation with one unknown, solve for that one unknown. Once we know what x is, we can go back to either one of those and solve for y. So now in equation 1, we got 2x minus 3y equals negative 13. Okay, so now we just have a very nice one variable linear equation. Again, just be careful with your order of operations, right? You're going to do multiplication before you do that subtraction. These are where the mistakes come in with these problems. So we get 2x, and you could do what's inside first, or if you can do it all at once correctly, that's fine. I'm going to do it like this just to show. We get 6x inside here and 21. We're subtracting both of those to get negative 13. So we got 2x minus 6x minus 21 equals negative 13. We gather the x's together. We add 21 to both sides. We divide by negative 4, and we end up with our x value of negative 2. So now that we know x, we can plug this into either the original equations, either 1 or 2, to find y. All right, so I'll plug it into the first equation. We got 2x minus 3y equals negative 13, one variable equation. Like this. All right, so we get negative 4 minus 3y is negative 13. Negative 3y, if we add 4 to both sides, is negative 9, which leads us to y being 3. So our solution is the point x equals negative 2, y equals 3. That's the solution, and that's the point of intersection of those two lines. And if you wanted to prove that, you could graph this line, which was equation 2, You could solve this for y and graph that line, and you would see that that point is the solution. Another way to check is, again, just put in the point that we found, -2, 3, and check it, right? So here we just checked it with the first one, really, right? -4 minus 9 is -13, so that's true. In this one, we get +4 plus 3 equals 7, so we know we did it correctly. All right, so that is the substitution method. I'll tie my shoe here so I don't trip and fall. And we have another method that's called the elimination method. Now, sometimes when you try to solve for one variable, you're going to get, something kind of messy with fractions and kind of, not pretty numbers. So we have another method. It's called the elimination method. And the goal is the same. The goal is to create one equation with one unknown, solve for that one unknown, which allows us to easily solve for the remaining unknown. So let's look at an example of this. We'll look at a couple, one easier than the next. So the first one, number 20, page 527. Again, the goal is the same. We're given a system of two equations. This time we have x plus y is 6, equation 1, and x minus y is -2, and we'll call that equation 2. So that's a system of two equations with two unknowns. Now this one we could easily use the substitution method to solve this, but we want to illustrate the elimination method. And this is probably the simplest case of the elimination method, because as what we're going to do here is, sometimes this is also called the addition method. You might see addition method in your book or other books concerning this method. And both apply very much elimination or addition, because what we're going to do is, in this case, it's nicely set up so that if I add these equations together, the y's are eliminated. So there's where the words come from, right? We're adding the two equations together to eliminate one of the variables. And when we do that, we're going to end up with one equation and one unknown. Now, it's not always going to be set up like this, where we can just add them together and eliminate one of the variables. Sometimes we have to change one of the equations, or sometimes both of the equations. Because remember, if I have, say 2x equals 6, I know that 3 is the answer to that equation. If I multiply both sides by 2, it doesn't change the solution to the equation. Right? The solution is still 3. So I can multiply both sides of either one of these equations, or divide by anything other than 0, and still have the same x, y's that are going to solve the equation. So I can change these equations if I have to get to the point where I have this. 2y and -2y, or 3y and -3y, so that they will be eliminated. This is already set up. So here I'm just going to add these two together, x plus x, so I'm adding to get 2x, the y's are eliminated, and I end up with 4. So obviously a very simple one variable equation here. I get x equals 2, I plug that into either original equation to find y. Okay, so I'll plug it into equation 1 and say x plus y equals 6, so y equals 4. So my solution is the point 2, 4. That's my solution. That's the point of intersection of those two lines. If you were to graph those two lines, you'll see that they intersect at the point 2, 4. So this is an example, again, of a solution that has, or a system of equations that has a solution. So they are two lines intersecting, and the solution is the point of intersection. All right, so again, that was a very simple example of the elimination method, where it was already nicely set up. All we had to do was add the equations together, get a very simple one variable equation, solve for that, go to either original equation to solve for the other variable, and come up with our solution. So let's look at one that's a little bit more involved than that one. And we have to do a little bit more work to get to the point where we can add them together and eliminate a variable. So let's look at number 26. On page 527, and again we have a system of two equations. Equation 1, 3x minus 7y is 13. Call that equation 1. And equation 2, 6x plus 5y is 7. All right, so there's a system of two equations with two unknowns. And we want to use the elimination method to solve. Now again, either method will work. But notice here, if you try to solve either one of these equations, you solve this for x, you're going to get some fractions. You solve this for y, you're going to get fractions everywhere. So I mean, you can do it if you're comfortable with that. If you're not asked to use a particular method, you use either one of the methods. But whenever you see something like this where the substitution is not easy, given a choice, I generally probably 90% of the time go with the elimination method, if given a choice. So here, you eliminate either one of the variables, right? So you look at the x's, and at least 3 is a factor of 6. Right? So if I was going to eliminate the x's, all I got to do is change this equation, right? Make that a negative 6x, so that I can add it to this 6x and eliminate it. If I choose to eliminate the y's, I got to change both equations, which is fine, you can do that, but after you do a few of these, you're going to see which is going to take less time and effort. If you want to eliminate the y's, it looks like the least common factor would be 35, so you'd have to multiply this by 5 to get negative 35, and multiply this by negative 7 to get a negative 35. That would work too. But notice here, if you see the 3 and the 6, you want to notice that if you multiply the first equation by negative 2, right, multiply the first equation by negative 2, which we said doesn't change the xy's that solve the equation. We can do whatever we want to it as long as we're correct. We multiply everything by negative 2. So negative 2 times 3x, negative 2 times negative 7y, and negative 2 times positive 13. And that's our new equation 1, right? We just changed the form of it. It's still equation 1. But we don't have to do anything to this one. Sometimes we got to change both. But in this case, now we just put 6x, 5y, and 7. And now we're at the point we want to be to eliminate the x variables. So we add these two equations together. We get 19y equals negative 19 very nicely. We solve for y, and we get negative 1. Now we come back and put this into either equation, either 1 or 2. We'll put it into, I don't know, we'll put it into 2 this time, just to change things up a little bit, and solve for x. So we get 6x plus 5 times y equals 7. Hopefully at this point, pretty simple. One variable linear equation. We add 5 to both sides, and we divide by 6. And now we have our answer. Our solution is x2, y, negative 1. And that's the point of intersection of these two lines. If you were to graph those two lines, you will see that they intersect at the point 2, negative 1. All right, so that is substitute, or that is another example of the elimination method. 2, negative 1, correct, okay. All right, so now there's a couple, we haven't seen any of the other two cases, right, where there's no solution or an infinite number of solutions. So let's look at how that's going to look when you try to solve a system. How are you going to determine that it's one of those other two cases where there's no solution or infinite solutions? Okay. So let's look at number 32, page 527. It's the same question. We're saying attempt to solve this system of two equations with two unknowns. And this one's set up for substitution. It already has a y in terms of x. Okay, so especially if the system is given like this, where one variable is already solved in terms of the other, that's a good clue to use the substitution method. You could switch this around and use elimination. Again, either method will work in any situation, but after you do a few, you're going to start to see which way is easier. This one already has y in terms of x. So now I'm going to just plug y equals 2 minus 3x into the other equation, right? This is equation 2. Plug it in. If I just plug it into this equation, I get 2 minus 3x equals 2 minus 3x, and it doesn't help me. So that's why we got to make sure we plug it into the other equation. So here we get 6x plus 2y, and the y now is 2 minus 3x. And we know that that equals 7. Okay, so now we try to solve this just like we did in the previous example. And we get 6x plus 4, right, 2 times 2, minus 6x. So again, this goes back to chapter 1 when we were talking about equations, conditional, inconsistent, and identities. And we said if you try to solve the equation, and the variables disappear, and you end up with what is a false statement, right? If you leave the equal sign in there, it's false. That tells you that there's no solution. And that the two lines are actually parallel lines. If we were to graph these, there's no solution, the two lines are parallel, and they never intersect. Okay? So if you try to solve the system, and you come up with a false, the variables are eliminated, and you come up with a false statement at the end, that's no solution. And again, this is very similar to what we talked about in chapter 1. The next example is if we come up with a true statement, right? If you got 4 equals 4, or 7 equals 7, then that tells you it's the third case where the two lines are actually the same line, and you have an infinite number of solutions. Let's just quickly look at one of those. Something like number 37. Okay, so same question. We got x plus 3y equals 2, equation 1, and equation 2, 3x plus 9y equals 6. All right, so this one, again, use either method. Since we got the x by itself, let's solve equation 1 for x. To get x equals negative 3y plus 2, and then plug that into the other equation. So I get 3 times x plus 9y equals 6. So negative 9y plus 6 plus 9y equals 6. Notice the y's cancel out, and I'm left with a true statement. Okay? So if it's true, that means infinite number of solutions. So that's our third case. Okay? So true statement, infinite number of solutions, variables are eliminated, false statement tells you no solutions, the third case when we get solutions. Anything else there? Oh yeah, we want to do cost analysis, revenue, cost, and break even. So this is just an application of what we just learned and what's going on here. So this is a, say, cost break even analysis. So a lot of times, people are starting a business. Obviously, start a business, you want to make money, right? So let's say we're looking at something like this, where we have, I guess we'll just call it X and Y. And we have a cost function and a revenue function. So when we say C of X, we're going to say that's the cost of producing X items, whatever it is you're producing, right? Cars, shoes, dishwashers, whatever. That's the cost of producing X items. R is the revenue. Okay, revenue is what you bring in for selling each item. So revenue is the revenue from selling X items. All right? So generally, when you start a business, there's going to be some sort of overhead cost, right? Like you got to rent a building or rent a truck or something, some sort of overhead before you even start your business. So let's say this is money on this axis, and this is the X that we're talking about here, X items of whatever the item is. So the cost generally, let's say, you're going to have an original cost before you even produce any items. And we're talking about linear functions here, so we're going to stick to straight lines. So we have some sort of cost that as you produce more and more items, your cost is going to keep kind of rising a little bit, right? So we'll say this is the cost function. Revenue is the money you bring in, right? The money that you bring in from selling. So if you haven't sold any items, you're starting at zero, right? So we got zero here. Let's say, oh, I don't know, 100,000 to start your business, just making up a number there. But the revenue, you don't have any revenue until you start selling items. And then, after you sell some items, you're bringing in some money. Hopefully, at some point, the revenue is going to exceed the cost. Right? So up until this point, we'll call this X sub 0. From here, you're operating at a loss. Right? Your cost is more than your money coming in. It costs you this much, you've brought in this much, this is how much you're losing at that point. But over here, you're starting to make a profit. Right? So many times we're concerned with this point. Where is this point where we start to break even? And we go from losing money to making money. So that's what we're doing here. And again, look, this is just a system of two linear equations. One line, two lines. We're looking for the solution. That's all we're doing. So let's look at one of these. All right, so I'm looking at, let's look at number 62. Number 62, page 528. And I started with a full piece of chalk. Damn. I know I brought another one. What did I do with it? I know I brought another one. I didn't go through two pieces already, did I? Maybe I did. Huh. Damn. Okay. 62. It says a company that manufactures bicycles has a fixed cost. So this is that original cost that I'm talking about here, the fixed cost of $100,000. And it costs $100 to produce each bicycle. Okay, so the selling price is $300. All right, so that's all the information we need. So we want to come up with this point. All right, we want to come up with what we call the break-even point. How many bicycles do we have to sell in order to break even and start making a profit? So we got to come up with a cost function. So we'll call that C of X, and we'll let X be the number of bikes. And we're going to assume produced and sold. Produced. And we're going to assume that the bike we produced is sold. Okay? So number of bikes produced and sold. For cost, it's going to be this original cost, and then $100 for each bike. So $100,000 plus 100 for each bike. Revenue is 300 per bike. Right? Each bike we sell, we get $300. So there we go. All we got to do is set these two equal to each other and solve for x to get our break-even point. So break-even occurs when the cost equals the revenue. So we set those equal to each other and solve. 100,000 plus 100x equals 300x. And that's hopefully pretty easy to solve. We isolate the x's, subtract 100x from both sides, and that looks like, what, 50? Right, is that right? 10, 2,000? No, 500. 2,000, 20,000 times 500. So we got to produce and sell 500 bikes in order for this business to start making a profit. And that is break-even point. Now let me see, there's one more. Sometimes you have to change words into the equations. That's kind of the last element of this section. So let's just look at one of those. And this will go for both this section and the next. We'll do another one in the next section also. The next section is 3 equations with 3 unknowns. Here we're dealing with 2 equations and 2 unknowns. So something like number 44 here, where you're not given the equations, you have to come up with them yourself. So number 44, it says the sum of 2 numbers is 2. So you got to come up with the equation yourself there. The sum of 2 numbers is 2. So that's not given to you, you got to come up with that yourself from translating the English sentence into algebra. And then it says, if one number is subtracted from the other, the difference is 8. So one number subtracted from another number is 8. So in this case, we're assuming x is larger than y. If you don't have to write that, but if y was larger than 8, you could put y minus x equals 8. You'll get the same 2 numbers. They'll just be switched, right? But they'll be the same 2 numbers. So here we have 2 equations, 2 unknowns. Sum of 2 numbers is 2. If one number is subtracted from the other, their difference is 8. Find the numbers. So you got to come up with the equations yourself and then solve it using either method that we talked about. And this one's, again, pretty easy. Set up for the elimination method. We can just solve that very easily. Add those together. Add the 8 and the 2 together. Get our x. Plug into either original equation. And we get 5 plus y equals 2. So y is negative 3. So the 2 numbers, and these aren't, we're not talking about points of intersection here. You would just ask, what are the 2 numbers? So these are the 2 numbers. And then, of course, you can always check, add them together, make sure you get 2, subtract negative 3 from positive 5. 5 minus a negative 3 gives you 8, so you know that it's correct. All right, so 5.1, we covered substitution method, we covered elimination method, we did cost revenue analysis, and we dealt with word problems.